introduce you to Professor Rubens Sampaio from the Catholic University in Rio de Janeiro, PUC-Rio. Professor Sampaio is an authority in uncertainty quantification, and he actually organizes one conference, which is already in the third or fourth version of this conference. And the next one will be in Santa Catarina next year. April. And he just reminded me that the deadline for abstracts is tomorrow. Right?
Tomorrow.
So, so yeah. So please take a look at the website and think about submitting a paper to this very nice conference. So please, Rubens.
Thank you. I would like to thank the organizer. Well, I prepared something on the supposition that is a large public and you don't have a lot of contact about smooth modes. It's a concept that is not standard in mathematics. So I put a little bit of history. So let's see how the thing goes. So I'm going to make a review of Karhunen law. That's the start of everything. Then another history of the smooth modes, smooth orthogonal decomposition. And now in modal analysis, that was the thing I was supposed to present here. And I'll talk a little bit about noise sensitivity. That was the thing that enabled one to use this from the start as a modal analysis tool. After this noise sensitivity study, we could solve the problem. So I'll show you some of the things we did, and I'll do some conclusions. For me, it was very interesting to prepare this presentation because I had to recollect my history with the subject. I was first exposed to the subject in 2000 by a friend of mine called Hans Droger from the University of Vienna. And the first time I saw this, I was disbelieved. I couldn't accept the things he told me about. So I started thinking that the thing could not be true. And after more or less 6 months of study, I changed my mind. It must be true. And I started to work on the subject. So I'll show you some of the history of Karhunen law. What's the main idea of Karhunen law decomposition? What's the mathematical problem? And this part here will not show you. So what's the history of this? The history of this is this thing starts with the statistics and probability and the people who work with functional analysis, spectral theory, and Hilbert spaces. So a lot of guys, Kozambi, Love, Karhunen, Pugachev, Obukov, they did all the developments from, let's say, the middle of the Second World War to 54, and no one used this. That was something that was developed. The main idea was to allow parametrization of a stochastic process. So if you have a stochastic process, it's something that's infinite dimension. You want to change this stochastic process for some set of random variable. And the standard way to parameterize the stochastic process is to do a Karhunen law decomposition. I'll show you how this comes. And these people here, they were interested in the theoretical problem. So they they did not give an application for it. So when in 67, a guy named Lumley, he applied this to turbulence. What was his idea? He looked at a turbulent flow, and he realized that there was something that was coherent. That means something that's completely stochastic had some information that was a coherent information. And he tried to make this precise. And the idea of this coherence is exactly what one calls the Karhunen law modes, are what's coherent in something that's stochastic. And this thing was 6-7. Then what was missing, there was a way to compute the Karhunen law modes. It's called direct method, but people need another way. And I don't have time to explain to you why. And in 87, this guy, Sirovich, came about with snapshot methods that you saw the application here in the morning. So he developed the snapshot methods, and this thing today is a very important tool. You have two methods that are, in some sense, they are, let's say, one is the complement of the other, and with these two methods, one can apply this in a lot of problems. In 96, these three guys, Holmes, Lumley, and Berkos, these are the guys from the dynamic systems. They wrote a book. That's a very nice book. And this book is about turbulence. At this time, there was no application in solid mechanics. So everything was in turbulence and solid mechanics. There was an application. When I start this, I look in the bibliography. There was about, let's say, 20 papers, no more. Today, perhaps, is 2,000 or more than this. OK. What is interesting, in this time, a lot of different fields applied the same techniques, but they called by different names. So one can hear the name principal component analysis. That's the people from statistics, image process. Empirical orthogonal functions are people in oceanography and meteorology. Factor analysis, data analysis, reduced model, a lot of different names. All this mean the same thing, mean Carnot-Loewe decomposition. SVD is a Carnot-Loewe decomposition in finite dimensions. OK, what are the two main purposes of the Carnot-Loewe decomposition? First is order reduction, by project the high dimension data in a lower dimension space. But here comes the important point. With Carnot-Loewe, what you do in the beginning, you say, OK, I want to make the best representation with 3 modes. I just allow 3 modes, or 4 modes, or 5 modes. And the Carnot-Loewe is for this. You want a small model, and you specify the number of modes you are going to use. And the second point is to fit restriction by revealing the relevant but unspecified structure hidden in the data. Is the thing I called about coherent structures. So with Carnot-Loewe, one wants to reveal what are the coherent structures. OK, now I am saying the same thing in a different way. So you read, I'm not going to repeat. And what's the mathematical problem? The mathematical problem is you have an ensemble, UK, of scalar fields, just in order to simplify the thing, I'm talking about scalar field. But of course, you can apply to vector fields. And let's suppose that these things are function defined on AB, and they belong to this Hilbert space. And what you want is to make a representation of this sort. Let's say if the thing depends on time, AK depends on time, and the other part depends on space, and this thing will be the Carnot-Loewe modes. So that's what you want to do. And it's easier to understand the problem if you talk about mathematics. So what you want to maximize is the mean of this thing here. That is the projection of U in the modes normalized. So if you write this problem as an optimization problem, that's the function you have to optimize. You have this thing here, and you have the constraint. And in order to maximize this, you have to solve this problem here. Is a eigenvalue problem. So you want to compute the psi, the modes, and you want to compute the lambda. I call this the energy. And the name energy comes from turbulence, because the modes will be a sort of velocity fields, and the lambda, where connect with the velocity fields, will be the energy of the flow. And what is interesting at this thing here gives you an idea of how good is the representation. If you sum this energy, you are going to have a good idea how you are going to represent your field. Okay, this R that appears here is this correlation between U in 2 points. Okay, so how do you construct the Karunilov basis? You construct first the correlation, then you solve this eigenvalue problem, and you write an approximation of the field, like this one. So in order to construct this, you have to subtract the mean, then you put again the mean back, and that's your representation. And to make prediction of this, you use a Galerkin method to approximate your solution and use this psi as trial functions. So just to have you an idea, let's suppose you want to approximate this parabolic equation here. You have initial condition, boundary conditions. So what you do is you propose a solution, and you have here the error of the you made in the approximation of the equation, the error in the initial condition. You approximate the boundary condition exactly. So you get a system like this, you solve, and you get the approximation of your problem. We have an idea of this. He showed us in this morning. So, okay, now I am in my topic. I am going to talk about smooth orthogonal decomposition. So this thing, I started this, let's say, in the 90s. In the 90s, there was no smooth decomposition. That's one thing that started in 2003, I think, something of this. So, and I'm going to talk now in a subject that's modal analysis. So I expect when people here understand what I'm talking about, you have a vibration problems. You want to compute frequency and modes. That's the problem. So I'm going to speak in this context. So I change a little bit. So from 90 to 2000, one could identify the normal modes and the energy, but not the frequency. So that's the state of the art. One can do this only if one had some information about the Mace matrix. So that was not a good tool. And one could apply to conservative system just in the free conditions or which run the vibrations. Okay. In 2000, there was a big breakthrough because one could also compute the natural frequency. And this part I'm going to show you. So instead of just the energy and the modes, one was able to compute also the frequency. That's a very interesting problem because you had, in some sense, two ordering of the modes. The modes could be ordered by energy, but could also be ordered by frequency. And this thing gave some important tool to study vibration problems. And with this tool, SLD, one was not required to know something about the Mace matrix. And the same thing applied, so this thing does not change. And finally, from 2010 on, we got some new implementations. And these new implementations solve a big problem that we had here about noise sensitivity. And one was able also to make some quantification of uncertainties. That was an important step. And there was a lot of new application for this. So that's a sort of a history. What I'm going to show you is these two parts here. Okay, what are smooth orthogonal decomposition? Essentially, the idea is the same idea of Karunilov, so it's the same sort of thing, but one requires some smoothness. So what does one mean by smoothness? One means, well, that's what a projection is. I hope you know this. So what is the smoothness I'm talking about? The smoothness is this. You require that the variance of this field here be the smallest as possible. So one maximizes this energy, but one minimize the V dot. That means the thing's smooth in this sense. So now I require the two at the same time. So if one goes to change this, look at what the requirements are, one has to solve this maximization problem. And in the end, what one needs is the correlation at time 0 of the field x and the correlation of the velocity field. So if you have this correlation and you solve this problem, you have the thing. So in a sense, what's important now is to solve this eigenvalue problem. Look, now one has a different eigenvalue problem, and I start talking about fields. Now I change, I'm talking about matrix. I could do the same thing about fields, but I don't know why I decided to make the thing simple, and this thing is not appropriate because we have a lot of mathematicians. The thing, perhaps they will appreciate better if I put everything in the operated form. Now I put in matrix. So you have to solve this problem. When you solve this problem, the psi are the smooth modes, and the lambda are the smooth values, and the smooth modes, of course, are different from the Karuni-Love modes. OK, now I am going to talk about how does one use these two smooth modes to do modal analysis. So now I am going to talk about modal analysis. And this sort of modal analysis I'm going to do is called operation modal analysis. So what's the standard problem of modal analysis? The standard problem is you know the input and you know the output. And from the knowledge of the input and output, you want to determine the system. Now, operation modal analysis is not this. Operation modal analysis is this. You do not know the input, but you suppose the input is stochastic and satisfies some properties. And the only thing you know is the output. Is a method that is output-only information. And I want to determine the characteristic of the system from the output and some hypothesis about the input. So that's the problem. So I don't know this. I want to determine the system, and I know the output. Of course, one cannot use the same standard modal analysis tool because you do not know the input. So how does one solve this problem? So the first thing I'm going to show you is I can relate the smooth modes with the vibration modes. I'm going to show this in the next slide. And one can relate the smooth values with the natural frequency. So that's the thing that allows us to do modal analysis with this tool. So this thing is not completely correct, but it doesn't matter. The idea is the important thing. In order to do the thing OK, I would need a bit more time. So let's suppose you have here a conservative system. You have the mass matrix, the acceleration, the rigidity matrix, the displacement, the force. And this thing I can write this way here. And if I solve the eigenvalue problem for this matrix, I call the phi the modes, and I call the omega the frequency. So that's the standard problem in vibration. And what I want to do is to relate this with the eigenvalue problem I showed you before. So how does one do this? So I want to relate these two problems. That's my standard problem for smooth modes, this one. And that's the standard problem of modal analysis, the normal modes. So if I take the second part here, this thing can be written this way. One can show this. And if I substitute this by if I use the definition, is the correlation of x2 dot with x. So if I write this, x2 dot and x2 dot I had from here, you see? I had x2 dot from here, and x I know. So if I put this, I get this equation here. So I can, from this, I can compare, and I see that this thing here are the normal modes, and this thing here, the energy, is the inverse of the square of the frequency. So if I compare these two problems, I see that they have the relations. So I can, solving one problem, I can get results from the other. So that's a small example. I'm going to pass too quick because I'm going to repeat this in another condition. So one can, since I was going to speak to engineers, one has to show that the thing works. So the thing works. If you go, the thing works. But this method was very bad numerically. The error was very big. There was a big problem, and this problem was solved when we studied the noise sensitivity. So I'm going to explain to you what the problem was and what solution one gave to this problem. So let's suppose you have a system here, and the response of the system is Z, but I have here noise. Let's suppose white noise, and I measure the observed thing is the X. So I have as response Z. I have no control with omega. I have some hypothesis, but no control. And I measure X. So I want to compute the correlation. So I substitute Z by Z. I substitute X by Z plus W. And I suppose that there's no correlation between Z and W. Of course, that's clear. And I note that the covariance of this thing is the sum of these two covariances. And if I put this in a picture, what one has is this. The measured signal is this thing that I do not know, is the correlation of Z, and something that I do know, since the thing is a white noise, that has just the correlation of 0. So the problem is that at 0, I have a very bad situation because the noise is very high. Was this observation that solved the problem? After we observed this, and after 3 months, we had the problem solved. What was the solution? Okay, this thing is just, if you are doing measurements in a vibration lab, there is 3 types of measurements. You can measure the displacement, you can measure the velocity, you can measure the acceleration. If you want to use accelerometer, if you use a vibrometer, or if you measure. And each of these signals, they are different. So if you suppose that one is a white noise, the other 2 are not. So we had to compute what is the correlation of this other noise. I don't have time to explain to you, but one shows that is this. So what was the solution of our problem? The solution of our problem was, instead of using the correlation at 0, that was very bad, we start to use the correlation of tau different from 0. And the problem was, if the correlation is at tau, could one show that the same equations are valid? The answer is yes. One can show the same thing is true. And everything works. For example, in this problem here, I am measuring, for example, I am identifying the system 1,500 times. And that's very important, because if I am identifying the system 1,500 times, I can use the statistic, the law of large numbers, and I can diminish the error. And the thing works beautifully. And that's a method that we implement this method, and we work this in real time. So we do the method until we are satisfied with the error. That's completely different from the other methods that they have to have all the information and they do afterwards. We do not do this. We do in line. So, and now I am showing you the identification we made of the simple system. That's the identification of the first mode. And we had a bonus. When we solved this problem, the bonus was we could do some statistical analysis. So we could compute not just the fifth frequency, but we can do some sort of error measurements with this histogram. So you look here. The SLD, the analytic is 12. The thing that we compute with the old method is 1420, and that's the one we computed this new tool. And we did this for the first, for the second, compared the analytic with the RSL2, that's the modification, and the old method. So there was a large improvement. So improved a lot, especially if the mode is high. OK, so what I showed you is how to use SLD to do mode analysis. The sort of mode analysis we do is an operation mode analysis that you control just the response, not the input. And this identification is very simple and fast. Since we didn't have the time, I didn't bring you everything to show you an identification online. I could do this if I had some time more. And one thing I did not show you, we quantify the frequency, the modes, and also the energy of the modes. So there is a whole history about the energy of the modes, because that's the important part when you do nonlinear system. This is a tool for linear system. That was the part I showed you. But of course, it's a very important tool for nonlinear system. And I'd like to make a comment about this, because I start with the most complex problem. When I start doing Karun and Love, I was doing a problem that I had a beam, and there was a barrier, and there is impact between the beam and the barrier. And the Karun modes, they depend on the energy, the maximum energy you have in your samples. So they change with the energy. For example, if I put a maximum energy and I compute the modes, these modes are different if I, let's say, multiply the energy by 3 or multiply the excitation by 3. It's completely different. I didn't have time to show you this, but what is interesting is this. People start with Karunin mode, solving highly nonlinear problems because there was no, they could not do mode analysis. And what I showed was the path backwards. Since you have no mode analysis, you start to do something with the energy. And what I showed you is that if you have this tool for nonlinear system, you could do the linear system if you had the, let's say, the right treatment of noise. So that's what I have to tell you. Thank you very much.